Hi there, my name is David Wajc, and in this video, I'd like to tell you about my iCalc 21 paper, joint with Amin Saberi, titled "The Greedy Algorithm is Not Optimal for Online Edge Coloring." The title of this paper is a tribute to an earlier work of Barnoy, Motwani, and Or, titled "The Greedy Algorithm is Optimal for Online Edge Coloring." And if you didn't hear the distinction between these two titles, it's precisely the word "not" indicated in yellow above. Now, I'll shortly tell you about the distinction between the theses of these different papers, but first let me start with the problem definition. As a reminder, a k edge coloring of a graph is an assignment of one of k different colors to all of the edges, such that no vertex has more than one edge of any given color. That is, it's a decomposition of the graph into k matchings. So here, for example, we have a painter who has 6 edge colored this graph. If we were to change this pink edge to be green, then this would no longer be a valid edge coloring because the vertex V would have 2 incident green edges. All right, so it's trivial to edge color a graph by assigning each edge a distinct color. And so the natural question is, what's the minimum number of colors necessary to color a graph? What's the minimum palette size? And as it turns out, the answer to this question is most tightly related to the following graph parameter, namely the maximum degree, which we'll denote by delta. So a trivial observation is that any graph needs at least delta colors to be edge colored. And as it turns out, for bipartite graphs, this is also sufficient due to Koenig's theorem. Now for general graphs, i.e. non-bipartite graphs, this is not always the case. Think, for example, of a triangle. However, the next best thing is true, and due to Wising's theorem, we know that delta plus 1 colors always suffice for general graphs. And in general, determining whether delta or delta plus 1 colors are necessary for a general graph is NP hard. And on the other hand, on the positive side, these sufficient conditions can also, a coloring using the minimum number of colors, which is always sufficient, can be computed efficiently. Okay, but all of these references on this slide refer to the offline model of computation or existential colorings. In this talk, we'll be talking about online edge coloring. So here, instead of having the graph revealed to us in one go, we'll have the graph revealed piece by piece, either edge by edge or vertex by vertex, as will be the case in this talk. And what an online algorithm has to do is assign colors to each edge immediately and irrevocably upon arrival. So for example, if we consider a bipartite graph in a one-sided vertex arrival model, so we'll have vertices on one side show up first, we'll refer to these as offline vertices, and then vertices on the other side show up together with their edges to their previously arrived offline neighbors. So a node shows up, we decide which colors to assign it, to assign its edges. Another node shows up, we decide how to color its edges, and so on and so forth. And as usual, what we'd like to do is be as close as possible to what an offline algorithm could do, which is using delta or delta plus 1 colors. Okay, so if you think about this problem for maybe 5 seconds, maybe the first algorithm you'd think of is the greedy algorithm, which colors each edge when revealed with the lowest possible color not used by either of its endpoints. And if you think about it for another 5 seconds, or maybe pause the video, you'll see that this uses at most roughly 2 delta colors. And well, this algorithm is neither interesting to describe nor to analyze. But unfortunately, this aforementioned work of Barnoy, Motwani, and Or showed that, well, this is essentially all you can get. So it seems like I don't really need 20 odd minutes more of your time, but bear with me. And I'll argue that this is not really such bad news. And in particular, if you inspect the lower bound of Barnoy et al., you'll notice that the number of nodes that it requires is exponential in the maximum degree. Taking out logs and flipping things around, we find that this lower bound only works for bounded degree, or bounded, at most logarithmic degree graphs. And so what I'd argue is that instead of thinking about this lower bound as a multiplicative lower bound of 2, so 2 delta colors, you should really be thinking about this as an additive logarithmic lower bound. So the number of colors you need in an online setting is at least delta plus log n. And so the natural question is, can you do better if delta is, say, super logarithmic? And of course, this question was not lost on Barnoy et al., who actually conjectured that you can indeed achieve a roughly optimal coloring, a roughly delta edge coloring in an online setting, so long as the maximum degree is super logarithmic. Okay, I'll just point out this approximately equal I'll be using throughout to suppress finicky multiplicative 1 plus minus little order of 1 terms. Okay, so just contrasting this conjecture and the lower bound from above. The lower bound says that you need at least delta plus log n. This is still consistent with getting roughly delta colors so long as delta is super logarithmic. So in the previous slide, we argued that we have some bad news. Here we're saying maybe they're not so bad. And indeed, we've had quite a lot of good news on this front, with a lot of algorithmic results going closer and closer to this conjectured bound of Bernoulli. So the first positive result was for random order edge arrivals. In Fox 03, Agarwal et al. Showed that for a multigraph with maximum degree, which is super quadratic in the number of nodes, one can obtain a roughly delta edge coloring under random order edge arrivals. In subsequent work, Bahmani et al. Showed that you can still outperform the greedy algorithm even for simple graphs with only super logarithmic max degree. And earlier this year in Soda, together with Bhattacharya and Grandoni, we showed that you can achieve the best of both worlds, getting essentially an optimal edge coloring, so roughly delta coloring, for any super logarithmic max degree under random order edge arrivals. So for random order edge arrivals, the question is more or less resolved up to the exact little order of 1 terms. But in this talk, we'll be focusing on adversarial arrivals, and in particular, adversarial vertex arrivals. Now, what is known in this setting? So in joint work with Cohen and Peng and Fox 19, we gave an essentially optimal edge coloring algorithm using only delta colors for bipartite graphs with super logarithmic max degree. In the same work, we show that if the maximum degree is not known a priori, unlike for all the algorithms listed above, then the best one can hope for is an E over E minus 1 delta coloring algorithm, and we achieve exactly that, again, only in bipartite graphs. And so the natural question left open by this work from a couple of years ago is, what can you do for general graphs under vertex arrivals? Is greedy the best thing you could hope for, or can you actually get an algorithm that uses less than 2 delta colors? And in this work, we answered this question in the affirmative, presenting a 1.9 delta coloring algorithm for general graphs under adversarial vertex arrivals, so long as the maximum degree is super logarithmic, i.e. so long as the lower bound of Bernoulli et al. Does not kick in. All right, so in the next, say 17 minutes or so, I'm going to give you some idea of the techniques that went into this result, and then I'll summarize with some open questions. So there's a number of ideas that needed to be kind of revisited and maybe adapted to our setting to obtain these results. And I'll spend most of this video discussing these. Okay, so let's start with the following. So I'll remind you that when reintroducing the edge coloring problem, we pointed out that edge coloring is precisely the problem of decomposing the graph into matchings. So every color class is a matching. And this seems promising because online matching has been studied in depth over the years. And so a natural question is, can we port any machinery from the online matching literature to help us solve online edge coloring? And as it turns out, one useful abstraction for solving online edge coloring is the following kind of online matching algorithm. Let's say an online matching algorithm A is alpha fair if for every edge, the probability this edge is matched is roughly 1 over alpha delta. Now this nomenclature bears explaining. So let's think of the case of alpha equals 1. If we talk about a 1 fair algorithm, then this algorithm matches each edge with probability roughly 1 over delta. Now this is the highest uniform lower bound one can give for the probability of each edge to be matched. If you consider a vertex of degree delta, then each of its edges, we can only match one of its edges for any realization. And so at least one of these edges has probability at most 1 over delta of being matched. So one fair algorithm is just an algorithm that gives the highest uniform probability for every vertex to be matched. And an alpha fair algorithm is just a multiplicative relaxation of the same notion. Okay, so hopefully we're clear on what an alpha fair algorithm is. How does this relate to edge coloring? Well, as it turns out, there's a one-to-one correspondence between alpha fair matching algorithms and roughly alpha delta coloring algorithms. And why is this? Well, okay, one direction, the backwards direction is fairly immediate. Run your favorite alpha delta coloring algorithm and just sample one of the colors at random. In that case, each edge will be matched with probability 1 over the number of colors, or roughly 1 over alpha delta. That gives us an alpha fair online matching algorithm. The opposite direction is a little more involved. We'll refer to this as the color peeling technique introduced in our work in Fox 19. But for now, let's just take this at face value. If you have an alpha fair matching algorithm, then you get a roughly alpha delta coloring algorithm. Now, the way we used this a couple of years ago, the way we used the forward direction of this correspondence is as follows. We relied on the online rounding scheme implicit in our work in SODA 18 of Cohen and Wajc. Apply this rounding scheme to the fractional matching, which assigns value 1 over delta to each edge. And this allows us to match each edge with probability roughly 1 over delta. So it gives us a one fair algorithm. Now, using the forward direction of the above correspondence, this gives us a roughly delta coloring algorithm. Now, unfortunately, the rounding scheme of Cohen and Wajc only works for bipartite graphs. And so this result was really restricted to bipartite graphs. And so the natural question is, can we somehow lift results from bipartite edge coloring to general graph edge coloring? And for this, we'll revisit a fairly old technique of Karloff and Schmois from the late 80s, who came up with this approach in the context of parallel algorithms. And this reduction from general to bipartite graphs can be stated as follows. If you have an alpha delta coloring algorithm for bipartite graphs, then you have a roughly alpha delta coloring algorithm for general graphs with superlogarithmic maximum degree. Now, since we'll need to revisit this reduction in a little more detail, let me unbox this theorem on this one slide pictorially. So as the title of the slide suggests, we start with some random bipartition where we assign each vertex either to the top or to the bottom independently, uniformly and independently. And the first thing we do is use our bipartite coloring algorithm for the random bipartite graph we obtain from this random bipartition. Okay, so we color the edges like so, and then we just recurse on the uncolored edges. Okay, good. So where are we using the fact that this graph has superlogarithmic maximum degree? Both the random bipartite graph and the recursive subgraph have maximum degree roughly delta over 2 with high probability. Reason being, every vertex of degree close to delta expects to see roughly delta over 2 of its edges cross the cut and the rest remain on the same side. And since this is the sum of independent variables, this is sharply concentrated. Good, so this very simple approach gives us the following recurrence relation for the number of colors needed to color a graph of max degree delta. We first use roughly alpha delta over 2 colors for the bipartite subgraph, and then use T of roughly delta over 2 colors to recurse. Solving this gives us alpha delta colors. Great, so as I said, this reduction of Karloff and Schmois, they used in the context of parallel algorithms, but the same approach works in an online setting. So before running your algorithm, you just pick which vertex goes to which sides, or maybe when a vertex shows up, you flip a coin. And in that case, it might seem like we're basically done. We already know a roughly delta coloring algorithm for bipartite graphs, this one. And so you might wonder, why am I telling you about a 1.9 delta coloring algorithm, where it seems like I should be able to get a delta coloring algorithm from the random bipartition approach? Well, unfortunately, this algorithm of ours from Fox 19 only works for bipartite graphs under one-sided vertex arrivals. Now, what do I mean by this? As before, we first have vertices show up on one side, and then vertices show up on the other side. However, this random bipartition approach needs to randomly assign the vertices to different sides. So we can't assume that the vertices of one side of the bipartition show up before the others. Indeed, there's an exponentially small probability of this happening. So really what we need for this reduction obtained by the random bipartition approach is an algorithm that works for two-sided vertex arrivals or interleaved vertex arrivals. So, we might have a vertex drop at the top, then a vertex on the bottom, another vertex on the bottom, maybe one at the top, maybe another one at the top, maybe one at the bottom, and so on and so forth. Okay, so if we have an algorithm for bipartite graphs under two-sided vertex arrivals, then we get essentially the same number of colors for general graphs under vertex arrivals. And what we show in this work is precisely a better than greedy algorithm for bipartite graphs under two-sided vertex arrivals, which, using the random bipartition approach, will give us essentially the same number of colors for general graphs under vertex arrivals. All right, so for the last technical part of this video, I'm going to tell you what goes into this result, which I think might have broader applications than this one work. Okay, so the last ingredient we need is a rounding scheme as follows. So our key new technique is an extension of a rounding scheme from a recent joint work of ours with Papadimitriou and Polner in EC of this year. In that work, we addressed somewhat stochastic setting, but in particular, we studied online matching under one-sided vertex arrivals. And what we show in this work is how to extend this to bipartite graphs under two-sided vertex arrivals. A little more formally, the new technical tool we introduce is the following. We introduce an online rounding scheme S, which given a bipartite graph G and fractional matching X revealed under two-sided vertex arrivals, matches each edge E with probability XE over 1.9. Okay, so the dynamics of the input are as follows. Vertices show up together with their edges and X values associated with these edges. And this rounding scheme decides whether or not to match an edge when it arrives. Another vertex shows up with a few edges. We decide whether to match here or not, and so on and so forth. Okay, so before telling you what goes into this theorem, let me tell you why this implies our main result. So first, we can apply this black box theorem to the natural fractional matching, which assigns values xe equal to 1 over delta for each edge. And what we get there is an online matching algorithm which matches each edge with probability 1 over 1.9 delta. In other words, we get a 1.9 fair algorithm for bipartite graphs under two-sided vertex arrivals. Plugging this into the color peeling technique, we get a roughly 1.9 delta edge coloring algorithm in bipartite graphs, again, under two-sided vertex arrivals. And then finally, plugging this into the random bipartition approach of Karloff and Schmois, we get a roughly 1.9 delta edge coloring algorithm in general graphs under vertex arrivals. All right, so if you're watching this talk and you've had enough technical detail, you're welcome to skip to the open questions part of the talk. If not, and you're curious about what goes into this theorem, I suggest you stick around. So here's the rough outline of what goes into this online rounding scheme. So I'll give you the broad brushstrokes, both of the algorithm and of its analysis. So when a vertex V shows up, we also have revealed its edges to its previously arrived neighbors, together with their X values. So what we'd like to do is, match V to each of its neighbors with probability at least, well, the first neighbor say probability 0.3 over 1.9, the second one was probability 0.4 over 1.9, and so on and so forth. So what we do as a first step is have this arriving vertex V pick a neighbor U with probability which depends on X, some formula which we will not discuss here. And this choice will be made in a non-adaptive fashion. So in particular, the probability that V picks U will be independent of whether or not U is free, i.e. unmatched. And this will allow us to pretty quickly give a lower bound on the probability that V picked U and it is matched. It's just independent. So when picking, we don't check whether or not U is free. But then, before matching, we need to check whether or not it's free. So if it's free, we match them. Okay, so we'll match U and V. This first step already gives us a non-negligible probability of matching U and V in terms of XUV. Unfortunately, it doesn't give us something as high as XUV over 1.9. It gives us something actually a little worse than XUV over 2. And so what we do is we use the fact that our choice was non-adaptive and we just repeat the process one more time. So if V wasn't matched after its first pick, we have it pick another neighbor, and then we match them if they're free. And what we want to show is that this second pick increases the probability of V to be matched to any one of its neighbors. So we could match U and V as a first pick or as a second pick. And together, this will give us a large, the claimed marginal probability of being matched. Now, what we need to avoid, or what we need to show, is that the match status of neighbors of V is not too strongly positively correlated. So in particular, we want to argue that the first pick that V makes, this vertex U, should not be matched if and only if all the neighbors of V are already matched. Okay, and why do we need to argue this? If all the neighbors of V are perfectly positively correlated, as an extreme case, then if V picked a neighbor as its first pick, and this neighbor was already matched, well, that will also be the case for all the other neighbors, and the second pick will not increase the marginal probabilities of V to be matched to any of these neighbors. Okay, so we need to argue that these different neighbors are not too strongly correlated. And what we show is, indeed, this is the case. These neighbors' match status are not negatively correlated, but they're not very strongly correlated. In particular, we show that their match status is the sum of negatively correlated variables plus low probability events. So all in all, you can show that their correlation is somewhat bounded. And using this, we can show that the second pick of V will actually increase the marginal probabilities of all of its neighbors to be matched. Okay, so this is a very impressionistic picture of what goes into this, what I think is probably the most technically interesting part of this work. I welcome you to read the paper and find out more details. And now let me summarize. So what do we show in this work? Our main result is an online 1.9 delta edge coloring algorithm for general graphs with superlogarithmic maximum degree under adversarial vertex arrivals. Now, this is by no means the end of the story for online edge coloring. Let me briefly revisit the results known in this space and point out some natural open questions. So as I mentioned before, for random order edge arrivals, we've essentially gotten the best we could hope to get, a roughly delta coloring for any superlogarithmic maximum degree. The natural question, or maybe like the holy grail of this line of work, is getting rid of this assumption of random order arrivals. So can we show any positive results under edge arrivals, or is greedy the best you can hope for under edge arrivals? For adversarial vertex arrivals, as I'd mentioned before, in Fox 19, we gave a roughly delta coloring algorithm for graphs with known superlogarithmic max degree. And for unknown delta, we show that the optimal bound is roughly E over E minus 1 times delta colors. And I should point out that this is the only work that also studied the problem with unknown delta. So all the other algorithms for this problem assume knowledge of delta, which I'll remind you is essentially the optimum value. Now for online algorithms, we're very often curious about the strictest possible model where we know nothing about the future. So it would be interesting to revisit this unknown delta, the stricter unknown delta setting for all these problems. Returning to what we show in this work, we gave a 1.9 delta coloring algorithm for general graphs with superlogarithmic max degree. The natural question is, how much better can we make this 1.9 term? Can we make it arbitrarily close to 1, or is there some limitation to what online algorithms can do? Is there some barrier that we cannot pass? On the topic of lower bounds, revisiting the lower bound of Barnot et al., they showed that for deterministic algorithms, roughly 2 delta colors are needed for any some logarithmic max degree. So I'll point out that all the algorithms that we know for this problem are randomized. So we don't know, except maybe for the trivial greedy algorithm, all the algorithms we know are randomized. And so the natural question is there some deterministic algorithm which outperforms the greedy algorithm for high enough maximum degree? Or alternatively, should we be strengthening these lower bounds? Related question, for randomized algorithms, the lower bound of Barnot et al. Only apply for delta at most square root log n. Now, hopefully you got a bit of a flavor of what goes into these results during this video, and you maybe got the same intuition that I have, that logarithmic is the right cutoff. So it seems that when delta is super logarithmic, or at least some high enough logarithmic term, we can apply to concentration inequalities. And that seems to be the real power of randomized algorithms for this problem. So I'd conjecture that this lower bound here is loose, and actually the right bound is delta, some logarithmic term. Finally, I'd like to maybe discuss something a little broader for online algorithms practitioners viewing this talk. All the results that we know for adversarial vertex arrivals appealed in one way or another to rounding schemes of fractional matchings. So this is given some results for online matching as well as for online edge coloring. And the natural question, which I find particularly appealing and would be interested to see more results in this space, is whether or not these online rounding schemes have further applications. All right, and with that, I think I've reached my time. I'll thank you for your attention and hopefully see you in a physical conference sometime soon.